chi-square test is used to determine if there is a significant difference between the observed and the expected results in an experiment. In this formula, the O represents the observed frequencies and the E represents the expected frequencies. Now, whilst this formula may look slightly confusing at first, we'll be going through an example, so hopefully it will make more sense. The null hypothesis in the chi-square test states that there is no significant difference between the observed and the expected data. The alternative hypothesis states that there is a significant difference between the observed and the expected data. Now, suppose we have a genetic cross between two heterozygous parents. We would usually expect the offspring to show a 3-to-1 ratio of dominant to recessive traits. The null hypothesis is that the offspring do follow this 3-to-1 ratio, whereas the alternative hypothesis is that they do not. Now, suppose we were to cross two heterozygous parents with brown eyes, we would expect there to be 3 brown-eyed children and 1 blue-eyed child out of 4 offspring. There are 5 steps in doing a chi-square test. The first step is that we identify our null and alternative hypotheses. Remember, the null hypothesis is always that there is no significant difference, and the alternative hypothesis is that there is a significant difference. The second step is to use the formula for chi-squared to calculate the chi-squared value. The third step is to determine the number of degrees of freedom, which is always n-1, where n is the number of categories. So after we have calculated chi-squared, we need to compare the chi-squared value to the critical value at the 5% significance level. Now, normally in biology, we do use the 5% significance level unless you are asked to do otherwise. This 5% level basically means that there's a 5% chance of incorrectly rejecting the null hypothesis if it's true. This also holds true for other significance levels, like the 10% level would mean that there is a 10% chance of incorrectly rejecting the null hypothesis. Now, comparing the chi-squared value to the critical value is what allows you to draw your conclusion. So if your chi-squared value is greater than the critical value, that means that you reject the null hypothesis, and there is a significant difference between the observed and the expected results. If your chi-squared value is lower or equal to the critical value, this means that there is insufficient evidence to reject the null hypothesis and there is no significant difference between the observed and the expected results. Now we're going to do an example where we have 2 yellow ranprees that we are crossing together and we are given the numbers of each phenotype. Now before we get into the question, I want to state something very important. This is a classic Mendelian dihybrid cross where we would expect a ratio of 9:3 to 3:1. And to work out what the expected numbers are, we have to basically add up all of the different phenotype numbers, 326, 96, when we get 560. What you want to do is you want to split the 560 in the 9:3 to 3:1 ratio, which would give you the 315, 205, 205 to 35. Just to clarify where this came from exactly, 9 out of 16 times 560 would give you that 315. To get the 105, it would be 3 out of 16 times 560, and that's where your observed values come from. First step, null hypothesis. So there is no significant difference between observed and expected. In this case, that the null hypothesis is that the observed ratios will fit the 9:3 to 3:1 ratio. It won't deviate from that. The alternative hypothesis is that there is a significant difference, so that your observed phenotypic ratios will not fit the 9:3 to 3:1 ratio. So to help us work out the chi-squared value, it's a very good idea to draw a table like this. So the first column is my observed values that we were given in the question. E is expected, that we worked out just using the ratio. We want to calculate the difference between the observed and the expected, so we subtract the expected from the observed, which gives us all the values in this column. What you want to do is square everything, so square 11 square minus 9, which gives you everything in this column. And our last column is everything in the O minus E squared column divided by expected. So that would be 121 divided by 315, 81 divided by 105, 9 divided by 105, so on. And your final column is the total of everything in this column, so 0.38 for 1 plus everything here. And this right here is your chi-squared value, so that's how you can use a table to help you work out the chi-squared value. So now that we have worked out our chi-squared value to be 1.2698, we can use this table to find out the critical value, the value that we compare our chi-squared to. Now the degrees of freedom is 3, so read across this row until you reach the 5% significance level, the 0.05, which gives us a critical value that I've circled here, 7.81. Now what you do is you compare the 1.2698 to 7.81. The critical value, 7.81, calculated chi-squared to be this. Now, because our chi-squared is less, in fact it's a lot lower than the critical value, this gives us insufficient evidence to reject the null hypothesis, which means that there is no significant difference between observed and expected results, which means that this indeed does fit the typical Mendelian dihybrid cross ratio that we'd expect of 9 to 3 to 3 to 1. Hopefully this video has explained something. If you have any questions, do drop them in the comments. Thank you very much for watching.